Hello, everyone. Welcome back to Talks for the 2019-2020 season. Thank you for making the trip here for what I'm sure will be a very exciting talk. We continue to collect affiliations of the folks who are making their way to the talks. I realize, though, as I'm talking to people, that this is dramatically out of date, and there are many, many, many people from many different places who are not represented on this slide. The purpose of this, of course, is just to give you talking points, and you can put your logo on the website and say, we too are Tux, and please feel free to reach out if you want to be listed as a member. Of course, we're particularly appreciative, and we'll speak about sponsors in a moment, but of course we're sitting in the space here at Autodesk Research, which is absolutely wonderful. And what's important to remember is this is largely the original population with some ups and downs of Tux. And it's important to remember that Tux, of course, is a community. And I love doing this, although I'm the only one who finds it interesting, but I do it every year where I sort of pan back and forth, and you just sort of notice that the colors of the logo for Tux come from the colors of all of the affiliations. So, you know, thank you for sitting through that again. But of course, the point is that this is not a top-down hierarchical organization. This is a community of people, and we want nothing more than to welcome all who are interested in human-computer interaction research in all of its different incarnations to come together and be part of the Toronto HCI community and to be here at Tux. I am Daniel Wigdor. I'm a professor at the University of Toronto and the chief scientist at Chatham Labs. With me also are Ali Mazalik from Ryerson University, Toby Grossman from the University of Toronto, and we now have, in addition to the editorial board, Fraser Anderson from Autodesk Research. Now, of course, the role of the editorial board is to seek out an interesting slate of talks to present to you each year, and that's our job. But of course, we are very interested to hear from the community about thoughts that you have, and we have sent out surveys before to solicit recommendations, and we always do. But that task pales in comparison to the real work of putting on the Tux series, and that is done by Shahzad. Where is Shahzad? At the back. Hi, Shahzad. From the University of Toronto, and also now Anita Kiwi from Chatham Labs. So thank you, Anita. I'll pass off to Ali now to talk about our series.
Great. Just remember what's coming next. Yes, the schedule. Wonderful. So once again, there's a few changes that you may have noticed for the coming year. Due to the kind of growing interest in the Tux community, we've really tried to focus down onto the standard series lectures. So we're inviting just the distinguished speakers this year to our lecture series, and as you can see, our community is growing. We have people all the way up on the stands over there. So kind of a second thing, I'll mention the schedule in a moment, but we'll be hosting this fall's talks in this space. But then in the winter semester, we'll actually be moving downstairs to a larger room to accommodate our growing community for the forthcoming talks. So again, these are up on the website. So these are the speakers. So today we'll be hosting speakers from Sidewalk Labs, which we'll hear about shortly. And then we also have speakers from France, from Microsoft, and from Carnegie Mellon. So we have an exciting set of talks. You can also join the mailing list and get information and reminders about all the talks. I should mention briefly our sponsors. We're very grateful for the generous support, first of all, of Stephen Sanders, who helps to make these events possible, Autodesk Research, Chatham Labs, the Computer Science Department at the University of Toronto, and that's it. I'll hand it over to Toby, who will tell you a little bit more about the website and the online materials.
Great, thanks. Welcome, everyone. I'm very excited about the next season of Tux. So, as Ali said, we have a website here. So all the information that we're talking about today, you can get there as well. One of the really nice things about the website is it links to our YouTube channel. And we're trying as soon as possible after talks to get them archived up on the YouTube channel. And you can go back and view all the past Sanders series talks that have been given over the last 4, or maybe is it 5 years? This is year 4, so over the last 4 years. So encourage you to do that. There's also a mailing list on the website that you can sign up, and you can see all the bios and abstracts of speakers that are coming up. So without further ado, I'm going to call up Fraser Anderson now to the stage to introduce our wonderful speakers for today.
Thank you, Toby. And forgive my notes, but we have a set of very accomplished speakers, and I didn't want to leave too much out. So it's my pleasure to welcome Siqi Zhu, Samara Trilling, and Brian Ho from Sidewalk Labs. To get into it, Siqi Zhu is an associate director at Sidewalk Labs, where he explores how technology can transform the design of urban streets. Prior to Sidewalk Labs, Siqi led a number of urban design projects, including the Boston Complete Street Guidelines, which won the 2015 APA National Award in Communication Design. He's also led projects for the Monterey Institute of Technology and Higher Education, which is Mexico's largest private university, the city of Grand Rapids, and MIT's Sensible City Lab. Across his projects, Siqi has developed interesting, novel, and aesthetic visualizations that clearly articulate his work. Siqi holds a bachelor's degree in engineering science from the University of Toronto and a master's in urban planning from Harvard University Graduate School of Design. In addition to all of this, he somehow manages to find time to teach as an adjunct professor at Northeastern University's College of Art, Media, and Design. All right, next. Samara Trilling. Samara Trilling is a software engineer at Sidewalk Labs. Prior to joining Sidewalk, she built city data infrastructure and visualization tools for Google Fiber's community impact team and iOS and web apps for Google News. She worked on original research into Columbia University's and New York City's ties to the slave trade. She has also interned for a number of state senators and House representatives. She graduated from Columbia University with a degree in computer science, specializing in artificial intelligence and a concentration in history. Last but not least, Brian Ho is a design associate at Sidewalk Labs, where his work focuses on bridging machine intelligence, urban futures, and human-centered design. As an interdisciplinary designer with a background in architecture, Brian focuses on making both the built environment and urban technology better for people. Brian's portfolio contains a wide array of inspiring projects, from an augmented reality interface for visualizing building performance to really cool ways of hailing autonomous vehicles. Brian received a BA in architecture from Yale University, spent a year at Columbia University's Master of Architecture program, and has a master's in design engineering from Harvard's Graduate School of Design. And he's also a lead AP building design and construction professional. So without further ado, please welcome our guests from Sidewalk Labs.
Can we start? Okay.
Oh, yeah.
Awesome. Thank you once again to Ali and Daniel for organizing, and the rest of the Tux group for inviting us. We're really, really happy to be here. Brian and Samara flew in from New York yesterday just to be able to do this talk, so happy to be here. One second. Of course, technology gets in the way. Great. We're going to, this is a fairly open-ended talk. We're going to spend today talking a little bit about our respective backgrounds, our interest in the intersection between technology and urbanism, and then end with a more in-depth discussion of one particular project, which I think will be of interest to the HCI audience. And just to kind of help you understand what we all do, so Brian and Samara are respectively computational designers, product designers, and engineers. They sort of sit on the more research side of the organization. I'm here based in Toronto. I work on project development, so I'm kind of more on the applied end of things, and my background skews more heavily towards planning, even though I also have a technology sort of background to all of it. I think this is actually a fairly typical cross-section at Sidewalk Labs. We draw from kind of across the urbanist technologist spectrum, and I think it very much reflects a kind of dual mentality that we have as an organization. So, as urbanists and sort of hobbyist anthropologists, we like to think of cities as kind of very inherently very complex creatures that are shaped by these kind of social and ecological processes, relations, human relations, relationships of power. For those of you who don't know, this is what is called a Noli map of Rome, dating from the 18th century, and it's a lovely example of the city as shaped by organic processes, and also the Catholic Church, as you can see, sort of at the footprints printed throughout. But on the other hand, as technologists, we conceptualize the city as a much more kind of mechanistic system, right? We think of the city as a data-rich field from which we can extract ever better understanding. We can categorize this information, produce knowledge, and with this knowledge, design better planning interventions in the city. This is sort of the opposite of the Noli map, the diagram done in the 1970s by a group called Archigram. We're not building this in Toronto, just in case you're worried about that. So I'd just like to point out that both of these kinds of conceptions of our work have a long history, right? So this sort of city as a technological machine idea really arose as a result of the post-war explosion of information infrastructure, and cybernetics. And there are many, many examples you can look at that is contemporary with this idea, right? So, you know, the Ameses did a famous kind of early multimedia installation in Moscow in the 1950s that basically started this idea of the city as an informational interface, right? Going on then to the development of many quantitative methods for analyzing and planning cities. This is Holly White. He was the pioneer that looked at categorizing, tabulating pedestrian behavior as data points as a way of informing our planning. And then going all the way to, and then this leads itself to computational observation and mapping, early GIS, and all the way to sort of our present day era of big data at the urban scale, and you know, frankly, the sort of valorization, worshiping of that data as sort of beautiful evidence, right? So this is the sort of work I was doing at MIT a few years ago. So then this idea that we can objectively know the city through better and better data then leads itself to the natural corollary, which is to say that we can plan the city better in a ever more automated, autonomous way. So if you look at early kind of planning pioneers, people such as Ian McHarg, he was one of the first people that developed this method of overlaying objective data layers, one on top of each other, as a way of justifying planning and landscape design decisions, right? So he looked at, for example, all of these different values, superimposed them graphically on a map, and then eventually kind of justified it in terms of a composite value, which then allowed him to make a quote-unquote objective decision about where to put a highway, right, next to River Valley. And other examples, computational, let's see if we can activate this video. So other kinds of work have been taking place at places like MIT with the Architecture Machine Group. So this idea that better data leads to better knowledge, leads to better design, is everywhere present in this sort of conception of how technology interfaces with the city, right? But I just want to circle back for a little bit. I think, you know, I think all of us know that's a fairly naive view, right? I think as fairly kind of sophisticated technologists, we know that technologies are full of biases. Technologies are situated in human relations and human processes. And even something as objective as data visualization in cartography could, in many ways, kind of perpetuate the biases and the biases of existing societal relations, right? So a good example, a very kind of on-the-nose example, is how Brooklyn was represented as being in decline in the post-war period. And this map became the famous map of redlining that then prevented investment in these urban neighborhoods. So again, sort of an objective view of the world that actually isn't quite objective, that then led to some real-world consequences. And then, you know, Samara and all of us had similar experiences kind of dealing with those issues.
Great, yeah, thank you so much, Siqi. So I really wanted to share an anecdote from my experience working with Google Fiber. Google Fiber was is still an initiative to give high-speed internet to all of America. And so as a software engineer working on Google Fiber, I led a team to help our community impact team decide where they were going to implement free and reduced fiber programs to the most digitally divided areas within the cities that we were going to serve. And so as an engineer, I think there's really a desire to think of decision-making processes as linear, where you would start with the boundary that you plan to deploy in. Within that, you do some data analysis to decide where the best areas to deploy these programs would be. You tell your program managers from the community impact side where they should do that, and then things carry forth from there. But in reality, and I think this reflects a learning process for me, was the community impact team had an understanding that just because the initial deployment zone boundaries were set here did not necessarily mean that was the be-all end-all decision. And if we found that there were some areas maybe slightly past the deployment zone boundaries that we really should be investing in, they expected the tool to tell them that and to break that rule that they had even initially encoded in that. So I think that was one of the first kind of realizations from an engineering perspective of how much this two-way decision-making needs to be encoded in the tool. There were also a couple of cases in which you would expect very cut and dry boundaries. For example, one of the first cities we deployed in was Kansas City, which is actually in 2 different states. You can see the Kansas-Missouri state line in the US runs right through that city. And so as the person who was creating the data schema for all of our geographic boundaries of where we're going to give service, that ended up being more of a philosophical question than you might anticipate as to whether or not a deployment zone had a state or not. And then finally, there are things that are very much part of the real and physical world that sort of alludes to what Siqi was talking about before with how cities grow, where they grow to, and turns out that Austin, Texas, another one of the cities that we deployed in, is built on a pretty huge brick of limestone chalk that makes it very difficult to deploy fiber underground, and so aerial is the way that you'd want to do that there. But that was, so each city becomes its own special snowflake, and it's a very place-based process of deploying a new city, which is not how engineering, is supposed to work in terms of easy scaling. So that was, I think, a real learning process for me as well. And then finally, policy and other sort of decisions that governments make, I think, have a huge impact on technological projects that have to do with places. So currently when you deploy fiber on a pole, you usually want the top spot. That's the best spot to have. But every other provider that has a line on that pole has the ability to wait 90 days to move their individual wire down. So you're waiting potentially on the order of months up to a year to get your spot to become available. And so One Touch Make Ready was a policy that allowed one provider to go and move all of the lines at once to make that go much faster. But that was something that was not engineering in the sense of software engineering, but still totally important to the decision-making process of where we're going to deploy.
So if as Samara's example illustrates, the question, the problem of applying technology to cities is not one of objectively coming up with the most objective way of coming up with the best solution, but rather a process that's much more contingent on values and policy in the past. What is then sort of our position in relation to the question of technology in cities? I have my own example that I'm always sort of very proud to come back to. And this was when, a few years ago, I was asked to develop the transportation master plan for the city of Boston and apply a objective sort of data-driven lens to that question. So what we did with that project is developing sort of, very kind of sophisticated data visualizations about questions of walkability and commuting time to begin to kind of point at questions, but rather than using these as an objective rubric for decision making, we took it back to the community to say, this is what we found, and what can you tell us more about why this is the fact on the ground? So it's our way of saying that the application of these technologies can in fact could in fact complement the sort of ethnographic richness that we as urbanists admire in city building processes. So to close this sort of intro, the core of the question we want to get to today is how are the sort of technologies that we're also interested in developing, and we do think they're very helpful tools for all of us, but how do we ensure that these tools are grounded in very human processes of decision making about building the city, and how are these tools actually help to extend human agency in that process? And I think that's a very relevant question for the human-computer interaction group. So with that, I'm going to turn it over to Brian to talk about one particular project that we've all been working on.
Thank you, Siqi and Samara, for that really, I think, excellent theoretic and contextual introduction to urbanism and computation. I think there's a lot of complexity and contradiction there, which is something we grapple with daily. So Samara and I are here on behalf of Generative Urban Design, which is a product effort within Sidewalk Labs. We are applying a range of computational methods and approaches to the problems of district scale master planning, urban design, and urban development. And I think what I want to say before we begin is we're not presenting a finished product. This isn't for sale. This isn't something you can log into today. We want to have a very open and honest conversation with you about what we've observed just through developing this tool, using it very lightly in some use cases, and then actually look to you in research, in practice, in other fields for how we might want to continue this conversation about this approach. I think before we get into that, though, I want to say also that it's not just a product, it's a team of individuals. Samara and I are just two members of a sort of wonderful team of incredibly talented and diverse personnel from urbanism, technology, and everything in between. So we have product managers, we have machine learning experts, we have data visualization experts, and then we have sort of a master of nones like myself. And of course, I think that reflection of an interdisciplinary team working together is seen at scale at Sidewalk as a whole, where we have over 100 folks comprising even more diverse backgrounds. So if Samara and I are engineering, product, and design, we work with Siqi, who speaks to development and planning. We have experts in mobility and urban systems. And it is this sort of wonderful chaos of so many professional opinions and perspectives coming together in one place that is, I think, really the potential of Sidewalk Labs, where we can actually cross some disciplinary boundaries that have existed for far too long. That being said, I think this is also the problem. So generative urban design as an approach is looking to solve for maybe one or two things. The first is this complexity and coordination problem. So urban development, as we've sort of seen, spans policy, it spans physical design, it spans infrastructure, there's engineering and planning and economics. And each of those sort of professional perspectives is typically isolated into either a consultancy or a specific service. And so everyone is running their own models, their own simulations. They're maybe talking to one another at points in the process, but they aren't truly collaborating at the sort of early points of a design. And so you tend to get sort of expensive mistakes and a limited set of possibilities that you're testing for. The other problem that we're looking to address is that of timescale. So I think we were just talking earlier about HCI being wonderful for sort of quick iteration. You can change a web interface and do an A/B test tomorrow and see what that does to your metrics. For cities, not so much. I mean, the timescale here is easily 5 to 10 years, and so you're really involved in a very slow process of guess and check, where we have some idea a decade ago, and a decade later we're going to find out if it works. So into that sort of problem space, I think we are positing, like many others in this room, that generative urban design can help as a method for fast simulation and optimization of results, where we can search a large number of possibilities in a design space or a decision space, and then help the user as the human understand what are the better options, what are the trade-offs implicit in that model. Are there sort of tensions between two competing priorities, or are there sort of correlations between things which are aligned? How this works for us as a process is that we register a number of inputs into our model. We then generate out of that model thousands, if not more, options for design. We evaluate them with simulations, which include environmental studies, mobility, pedestrian modeling, yield forecasts, and then use that information to basically run optimization over the entire process. So we apply Bayesian approaches, goal seeking, statistical models. We were trying a number of things to sort of get at better solutions. I think what I want to stress here is this is not a technical diagram, this is a designer's diagram of a technical system described to him by engineers, so full caveat. But I do want to walk you through what the tool looks like today. I think that will be a good basis for conversation. So we start with a site, right? So here we have a site looking for use. We have ingested from GIS sources some sort of registered site boundary in the world with some information about what we want to build there. That information about what we want to build is then registered to a land use diagram. It's a raster, it's an array of multi-channel values. And then we could begin to experiment with, well, what if we put residential, the red squares, in the lower left instead of the top right? There are so many options already in this decision space that we can begin to explore just doing this alone. On top of that, we layer a number of procedural algorithms for generating streets, so we can subdivide the space through parcellization techniques into rectilinear grids, non-orthogonal grids. We can try and test sort of subtle changes to street grids and types. We can then go in and place, again, both the built environment and the public realm. So here you're seeing in green open space, which might otherwise become a park or planted areas. And again, we are testing possibilities here. So you're looking at just one iteration, but there are thousands implied by this grid structure alone, and we can begin to search through that space as well. And from here, we get massings. And I want to let Samara talk about some of her evaluations.
Yeah, so from here, from those building footprints that we have, we can extrude those into actual built environment forms. So here you can see we're starting to get something that hints at what a district might look like. And you can also see that the diversity of buildings here is not very high. You can also see that the level of detail is not very high. This is, what we found is, I think, a lot of times we've talked about this a lot amongst a lot of HCI researchers, but when you give something that has too high a level of fidelity, often people fixate on the things that are not correct about that. And so that's been, I think, a learning process for us as we've decided how much detail to provide in these very early ideas of what the whole district might look like for building massings, knowing that we're not going to hand an architect or take over an architect's job, whose job it is to really create what the building is going to look like. And then from there, we run these objective functions. So this is an example of a visualization of an objective function around pedestrian mobility and movement. So the yellower spots there, the later spots, are places where there are more pedestrians walking. And this was part of we implemented this from a paper that we read that talked about the optimal level of buzz that you would want to have in an urban environment to feel safe and comfortable and like there were things happening, but not feel like there was no space on the sidewalk to move. So this is one output that we generate. This is another example of daylight. So how much daylight different parts of buildings would get over the course of a year, normalized for different seasons. And this sort of, in sum, represents, you get this large solution space with the film strip at the bottom representing all of the different iterations that were generated by this process. And you can see every step along the way can result in a totally different branch of city environments. And I think our goal here from an HCI perspective is really to allow users to make sense of this huge amount of information, to explore it in a meaningful way, and to allow them to visualize trade-offs between the objectives that they may be seeking. And so at this point, we normally talk about what kind of scoring function you're going to apply to this. You can obviously generate a lot of iterations and score them all, and then you've got your one generation, and that's fine. But the exciting part, and where I think a lot of computation can kind of expand the area that we're talking about here, is if you have a good score there, then you can apply Bayesian optimization, as Brian was saying. You can apply genetic algorithms and use many, many generations to see if you can get something that looks a lot more like the optimal district for that score. And the interesting thing is that often people, I think, you can feel free to correct me if I'm wrong, but in architecture, you're not necessarily, even in urban planning, you don't necessarily have these a priori ideas of which objectives are more important to you than others. You know they're all important, but if I said, tell me your percentage weighting for mobility and for daylight, I don't think that would be, it's not a known quantity. So that's where the sort of exploration really comes in. And as an engineer working with architects, I think there's a lot of problems that to architects and urban planners can sound really hard, but are actually easy to implement. So one example here is the optimization algorithms that we have. A lot of these are actually quite simple. There's existing libraries that are really useful. We use Python. SciPy is great. There's great optimization algorithms that you don't have to implement from scratch. And that's something that you can see the plethora of options that we got out of optimizing this, and you can see the score going up over time. Another thing that we found is that sometimes you'd want to get a sense for what the built environment's going to look like in a more photorealistic way because you have such low fidelity on your actual buildings. And so this is something we generated satellite imagery for a totally made-up city that will never be built. And that is something that took me and a colleague about 2 days to do with a couple of things. I'm going to go into how we did that a little bit later. But auto-generating satellite imagery is something that you would think would be difficult, but it's actually easy from an engineering perspective. Then there's the opposite, which is where we actually spend most of our time. What are the things that sound easy to architects and urban planners, but actually are really hard to get from an engineering perspective? So getting meaningful diversity of buildings that also look realistic is a huge problem for us that we spend a lot of time talking about. And partially it's because the question goes back to which rules do you break? You want something that looks realistic enough that you can imagine it in your city, but you also want to be able to evaluate, options that you've never seen before, and maybe we should build super tall, thin, twisty towers, and we won't know until we try that, but an architect looking at that might say, that's totally unbuildable, I'm going to reject that out of hand. And then the other sort of, I think, stereotype about engineering is it's really easy to just encode the entire legal code that exists for buildings in your algorithm, and that's the best way to make sure that your buildings are compliant. But at least in New York, I'm not sure about Toronto, basically any building that gets built will apply for exemptions to that code. So the code is really not so much the rules as sort of the some constraints that are all tweakable, and so you have to choose which rules to break. This is a little bit more information on how we generated the satellite imagery, and this was part of a hackathon. We do these dream sprints where we generate a bunch of possible ideas for projects and then work across the team to sort of separate from our day-to-day work, try those out. And they're not always productionized, but when they are, it's really cool. So here we use a convolutional neural network in the shape of a cycle GAN to, we initially started with a pix-to-pix model, which you can see on the top right. Actually, that's really low quality, and you probably can't see that at all. So I'll let you know. That is, it looks pretty fuzzy in a lot of places. There's a place where there's some empty space where we didn't actually have, we took screenshots of our tool that Brian showed earlier in like a Google Maps sort of format, and the pix-to-pix model is trained to take a map and turn it into a satellite image. And so that was all pre-trained. We fed in our map images and we got out our satellite images. And you can see that there's some spots where we had no map, and it sort of spontaneously generated things that look like garbage dumps in sort of a tiled way. So we moved to using this cycle GAN and came up with much crisper results that actually looked okay in isometric form too. If you sort of tilted the camera a little bit, you got a fairly reasonable satellite image out of that, so that was pretty cool. And then we did some extra work retraining that model to deal with tiling. So each of the images on top is only one tile, but if you do that, you end up with these seams that are pretty obvious that Google Maps does a lot of work to try to erase. And so we retrained that by taking out the center square and then retraining it to just be able to predict the edges. One question we get a lot is why would you not just use a neural net? You think you know what good cities look like. We should just take examples of great cities that we know, and you should train your model to take those and mash it up into something that's a combination of Toronto, New York, Barcelona, and something really cool. And I think for us, this is really a question of principle, right? Our job here is to radically transform cities, not to radically replicate things that already exist. And so we also wouldn't want to be in the position to dictate which cities of the world are the best from our sort of narrow and potentially sometimes incorrect viewpoint. So our goal here is really to allow the explainability of the model to drive humans to make not necessarily, make hopefully better decisions, but to be able to know why they're making the decisions that they're making, to have higher explainability, and ultimately to embed the human deeply in every level of the decision-making process here.
Great. I think that's a really excellent introduction to just some of the human problems that we find within our approach. And so I think to Samara's point, there are many struggles with just getting the two of us to talk to one another. But I think also the other side of it is talking to the user. So what does the user want? So we have developed an interface for the search and sorting and filtering of a large decision space. So some of the features you see here are things that you would expect. So histograms for understanding frequency distributions, scatter plots for understanding correlations. We have cards and charts to understand sort of the trade-offs implicit in this space. But I think what we're finding from developing these sort of very data-forward interfaces is that yes, this is the beginning of a successful tool, but it is not enough to really close the gap for what an urban design tool wants or needs to be. And so I think I will now talk to some of the UX lessons learned, and I think we'll take it just a conversation from there. And maybe the place to start is Toronto. So we have actually, if you haven't been, you're welcome to come, an office down on the waterfront called 307. And we use it as a public space for prototyping where you can engage with some of the tools that we're thinking about, experiment with some of the physical interventions, and leave feedback. And so one of those installations is actually a generative urban design explorer. It is a sort of large display with a number of dials, and what you can do is you can turn the dials to sort of change the inputs into the decision space and get an instantaneous result back. And I think we've discovered this is an amazingly engaging device. People love to interact with it, they want to touch it, they want to talk more and learn about the process. It really starts a conversation that we are really willing to have. At the same time, I think we also realize that there is subtle but important distinction between public engagement, co-design, and sort of public participation in the design process, right? The user is exploring a design space that we've created for them. They're not fully in control of the geometry or the dimensions of the design. They aren't really setting prioritize. So we're sort of letting them explore a space that we've created, and I think that is useful, but maybe not a fully functional design tool. Other experiments that we've done, I think Samara talked a little bit to our sort of practices around hackathons and design sprints. We actually did a week-long exercise with Dan Taeyong at Columbia University into sort of tangible media, right? And I know we saw some of your work earlier today, so this will all be sort of quite repetitious, but we're looking into ways in which you can use physical devices, real-time interaction, and sort of projection mapping to sort of bridge some of the problems that we see in design tooling. And so here you're seeing a selection of samples that we worked on, things that allow a user to move a sun around and see where the shadows fall. You can design a street grid with sort of a multi-touch of participation between multiple users. You can draw a building on a whiteboard and get back a 3D model that sort of reads that plan form to create a massing. I think all of these are incredibly interesting ideas, and I think what we want to do as a group is find ways to fold them back into the design machine that we have. And I wanted to quickly highlight one example that I thought was particularly successful. Here we have a series of fiducials taped to those little hexagonal building blocks that you see everywhere. And what the user is doing is they're placing massings that correspond to different housing yield, sort of different houses, different commercial offices, and they're adjusting a real-time gravity model. So we're simulating the demand for transit across the site. And there's something about just the interaction between physical object and real-time projection that is incredibly explainable without having to say anything. And we actually haven't been able to get to this level of intuition in other means. So I think if interaction is one of the things we identified, the other thing is that design is a hard process to codify. So you may think that it would be really easy to apply version control systems to urban design, and I think that's because we expect it to be sequential and sort of neat and tidy, like the graph above. But the reality is it's actually more like the graph in the lower half of the screen. It's this sort of parallel process where at any particular stage you're going to explode into 6 or 7 coincident options that all have to exist at the same time with different constraints, converge on them, and then diverge again. And that sort of process of going wide, going narrow, and going wide is actually quite hard to control and match. And if you're trying to optimize, well, if you're going to change your constraints every month, you're going to have a hard time optimizing over the long run. The other sort of insight here is around GIFs, and I say this half in jest, half seriously. We use them a lot in our presentations, and I think we do that because they're incredibly captivating, and we can sort of sell things off of them. But more importantly, I think GIFs are a reflection of the fact that we're no longer dealing with static design. So when Siqi and I went to school, we would draw a beautiful rendering or a plan document, put it on the wall, and walk away. And now what we're talking about is design spaces. We're saying, well, it could be any one of these 5,000 designs. They all follow the same rule sets and logics, but it might not be any one of them in particular. And so a GIF, sort of as a moving graphic, is an incredibly effective way of communicating what that design space looks like. What are the trade-offs implicit that we've made? What are the physical relationships between street grid and building form? How will this thing perform given a set of constraints that we might give it? And I think I want to end on a sort of prosaic note, and we'll see where this takes me. But we've also found that as we work with existing tooling in the design space, we're meeting people where they are, and where they are is spreadsheets. What we want to build is we want to build a collaborative, malleable, productive tool for many people to come together, work on a data-rich environment, create models, do regressions, do live updates to inputs. And what we found is that Google Sheets in the cloud is a pretty good analog for that. And so what we find that we are building more and more is a visualizer for Google Sheets. And we're going to meet Google Sheets sort of where it is, rather than have it come to us. And I think that's an interesting note, and I sort of want to leave that there, and we'll maybe talk about that offline. But I think it's an interesting observation as well. And so I think that sort of brings us to the end of this discussion. And we've put up here a set of questions that we have for the group. I think we're among sort of very august and distinguished faculty and researchers, and we would love to hear your advice. I'd also say that we're avid readers. We love research. We read papers weekly. So if you have things, send them our way, and we'll see what we can do. So thank you very much for your time.
you guys very much. There's time for questions. If people have questions, throw up your hand. We'll bring a microphone to you.
Hi. You've used the word optimize over and over again. In my experience, the more you optimize something, the more brittle it is. And it seems like a classic example of that is architecture, where architects design a beautiful building. It doesn't last through time because functions change, society changes, and so on. Of course, you could say you could add that to the objective function, but you didn't, and I don't know how you do it. But how do you address hyper-optimization, creating a very brittle system?
That's a good question. I think there may be a couple ways to address this. One is that we are thinking about modular systems, so it gets sort of into that design space modeling, right? We're not interested in one solution, we're interested to many. I think maybe, Samara, you can talk a little bit into the way we handle optimization for changing objectives. So we actually have started to do is optimize for multiple things simultaneously, and then sort of keep those results in parallel. Maybe that's a good segue.
I think that really gets to the heart of how it's so hard to define a score function that accurately represents everything that you want to come out of something. And I think a lot of the way that we think traditionally about optimization is that over time you make smaller and smaller adjustments to get to something that you feel to be somewhat perfect. And I think that's somewhat different from the way that we approach optimization. The way that we're thinking about this is we have so many possible options within the design space. The design space is so large that optimization is really about choosing which area of the solution space to explore next. And so the difference between things that are sort of mapped close to each other in the solution space may actually be quite large. And so you may have it's not so much that when you make small changes you get to something that can never be changed, otherwise it will break. It's much more about understanding how the sort of trade-offs between things, and in such a large solution space, you have to choose where to explore first. And for example, Bayesian optimization optimizes for exploring spaces that you haven't looked at yet, whereas genetic mutation would take two things that you have seen before and sort of make them combine them into something that's somewhat new and slightly mutated. And what we didn't say here is, in addition to optimization, we also have mutation, where you do make smaller changes, potentially even to existing architects' drawings, which is kind of the question that you're asking. And so I think that the goal is definitely of optimization, and we've seen this when working with architects. The goal is never to tell them what they should build. The goal is to give them enough understanding of how much of the solution space we've explored to give them confidence when they choose one particular venue to go down, that they know what is involved in that particular venue, because you can compare it to all the other options.
Going back to the beginning of the talk when you mentioned design can't be objective, and the Google Fiber example on the limestone, how would you suggest embedding those informations in the simulations? Because as of now, from what I understood, the simulations just give us the optimal way of building a city, but it doesn't take into account those backgrounds that maybe a city was built on something that would maybe cause issues, or even for the cycle again, when you're training it, it would just look at data RDO and not what's behind what we actually see as just numbers.
Yeah, that's a really good question. I think that with the Google Fiber example, clearly if we were running a simulation I was working on the community impact side of it, there were other folks thinking about whether we should use aerial or underground fiber. But I think that our model takes in, and we have an ever-growing list of inputs to our sort of pre-generation model. And that includes everything from existing buildings that are currently there, existing transit. We have the boundary that you're sort of considering to create new buildings within. And then it also includes things like the geology of the space, if that's something that you care about. And so ideally, I think, we draw on, especially for a lot of hackathons, we draw on data like OSM and things that are sort of community generated. And I think that I would hope that we can come to a place where we can just download the full list of layers for whatever area of the world you ever want. And that really goes into how you design your objective functions, right? What does your objective function rely on in order to predict what it should do? And in your case, obviously, yeah, had we been using generative design on Google Fiber's cities, I think we would have implemented geology there as well.
I'll just quickly add by saying that the reason why we don't consider generative design to be an objective tool is I think the way that's reflected is how we actually use the tool. I think, like as Samara and Brian's pointed out, we don't consider kind of singular outputs from generative design to be the optimal one. The role of this tool is really to radically open up the solution space for multiple stakeholders and actors within the collaborative design process. And this is also for those members of these stakeholders who are typically very bad at making actual physical propositions about what built form needs to look like on paper. So generative design, in a way, is a sort of a magic pen, in a way, right? You, by beginning with a few kind of scores and priorities, you open up, you all of a sudden have hundreds of options at your disposal. But then ultimately what ends up being the optimal one is going to be a collaboratively shaped process. We haven't showed a lot of that because I think that's kind of on the roadmap and something that we haven't actually quite actioned, but that's very much the aspiration. So, right, I would say that's accurate.
Yeah, absolutely. And I would often say that you'll get something that performs the best according to the score that you initially generated, and you'll be able to clearly see that was not what you intended to optimize for, and that's when you go back to keep iterating over your score function to make it more realistic to something that you actually want to build.
Thank you for your presentation. There are some more questions I could possibly ask. I could ask an hour-long question. I'm not even going to go into the privacy rabbit hole. But one of the things I find, and this is going back to the first question, is that today there seems to be a lot of belief in computer systems. And this is because we grow up with computer systems. We've never known a time when we didn't have computer systems. So managers love looking at their Excel sheets, and then the Excel sheet calculates the solution, and then they execute that. And everybody in the organization does that, turning us all into little robots. So there's good design. There's design by committee, and then there's design by computer. I think there's a real risk, and I think the first question asker already mentioned that if you do not include in your models the correct parameters, like I just looked up Hausmann, for example, he really radically changed Paris because of transportation, and he increased the number of nodes to how to get from one place to another. I noticed that in the video you had some markers, solution markers, and then some traffic going by, but I didn't really see that as being part of your equation. And I also noticed that a lot of your animations were kind of stuck in a local minimum, where it just kept doing the same thing, but just slightly different heights, taller buildings and stuff like that. So could you comment on, is there a risk of believing your tool? And should this not be something that's done after an urban planner goes this is what we're going to do, and now we're going to perturb the design that was done by the human? Because I think computers are very good at perturbing, changing.
Yeah.
That's a good point. Yeah.
No, I think it's a 100% valid point, and actually you have identified exactly the use case that we currently are exploring, which is around this idea of mutability of an existing design, right? So let the planner come to us with an option that they like, or even 4 or 5, and we can then do that sort of searching in that local space around how would you improve it? Should the floors be slightly taller floor to floor? Should the floor plates be a little wider? The sort of minute questions that a designer doesn't really have the time or resources to explore, but they've already voiced their inputs. So I think that's entirely valid, and we're very much aware of that.
Yeah, to speak to the mobility part of it specifically, so we've showed it, we I think our vision is to be able to have a huge array of potential objective functions, not all of which are built by us. I think the goal is to have this be something that any researcher, any students, anybody who has expertise in this particular space could write an objective function that says, give me your city and I will tell you how well it does on this thing. And that, I think, should be a community-driven process. That's not something that should be chopped down. And then you could have combinations of objective functions that you think would represent something. We talk about what represents happiness a lot and how problematic it is to try to codify that in one particular objective function, but how necessary it is to think about what the components of that are to make sure that you're not breaking any one of them. So I think that the goal is certainly not to, I think you're right, there's always a chance that whenever you define a solution space, you're always leaving something out. And I think that the goal is really to, as you sort of said, empower people to take one particular idea and say, oh, I hadn't thought of that. Let me go back as an architect and make a new design that sort of incorporates that idea and feed it back into, maybe there's some kernel of insight there that says that something that had this particular feature performed better on this one particular objective function, and then use that as a kernel of a new exploration sort of venue. This also gets back to what level of detail we use, right? We have like sort of 2.5D buildings, and we talk a lot about how it would look if they were more photorealistic, but that is something that we've chosen not to do for that reason, because I think it's a tool. I think the way that you use it is incredibly important to whether or not it does the right thing.
Thank you very much. I was just wondering, the examples that you showed, sort of very drastic changes, or building like entire neighborhoods from scratch, pretty much. I was wondering if you're exploring ideas like how to improve, let's say, mobility, for example, in a city that which you cannot just like reveal. I don't know, show like one of those pictures from Rome in the 1800s, and mobility in Rome is terrible, but there isn't much you can do there because you can just knock down, the city center. So is your house or tool, is it good for approaching those kind of questions, and have you worked on anything like that for now?
We've done some work around essentially scenario testing or sensitivity testing, right? So if I'm not out to build a neighborhood from like greenfield site, if I actually have an existing fabric and I want to make an alteration, we can evaluate and test the sort of 3 or 4 options. Or we can create a design space model, which is simply testing where you might close or open a street in the broader context. It need not be ground up, and I think we do tend to default to those graphics because they are slightly more legible at a distance, so to speak. But I think you're entirely right that there is a subtlety here where the application isn't always as open-ended as we might make it seem.
Yeah, I wanted to point out that there's a company called Replica that is much more centered around that particular problem of mobility and making small alterations to mobility systems within cities, which are often incredibly expensive and not something that you would say, let's just tear it all down and start over. So Replica, is using a lot more data about how people actually move around cities. This is, sort of a one attempt at that, but that is by no means our sole expertise. And they've really poured a lot of work into making sure that you have mobility models that work for existing cities so that you can accurately predict if you move this subway station, if you add a bike lane here, what the impact of that would be. And I think that actually is, I think it's really key that we point out that we're evaluating these objective functions to determine how well they predict real life, right? Some things like shadows, the sun's probably not going to change its position too much, but when you're talking about human behavior, there's a huge amount of uncertainty that's sort of involved in that, and I think that's totally crucial to the work that we do to have this be a useful tool. So we talk a lot about how to validate our objective functions in a way that makes sense.
Great presentation. Thank you for sharing that. The concept that I really particularly liked was the physical one, where you have the buildings and you could move them around. One of the things that I loved about it is that it showed the trade, in this case, the traffic. And for me, that was a very compelling way of telling people, it's not only about moving knobs and then seeing things grow, but, these are the implications of it. So I guess my question is, how are you looking at communicating trade-offs and making them part of your model as you move forward?
Yeah, I think ideally, it's almost exactly as you saw, right? I think the explorability of a physical medium is one of the best ways that we know to sort of explain that process. I think architects have long used physical models for that exact reason, because you can hold them up, look at them, move them around, and see them. I think we hit technical challenges where we can't simulate results fast enough to really allow for that intuitive feedback, and that's, I think, one of the hard problems that we're out to solve, and would love thoughts and comments on it. But yeah.
Yeah, this is, I think, an area where I would love to hear sort of more, I think that the physical aspect of that, where you can turn something and immediately see it move and then turn it back and have that respond really immediately, is totally key to having the trade-offs be intuitive, that you often, to be honest, don't get in a 2D computer screen. And so I think, we've run co-design sessions before. I'm really excited to see how we can use this in sort of to maybe explore we talked about exploring one small decision here, rather than, all of them at once.
Yeah, that's really kind of one of the hardest questions we're struggling with, right? Which is how do you visually represent the vast decision space that results from running something like this. And we showed some examples of kind of data-rich interfaces that lets you, in very conventional ways, frankly, kind of measure trade-offs between different measures. But yeah, it's a hard one. Yeah, I don't know. We'd love any feedback and ideas you have on that particular question. So,
one up in the nosebleeds.
Hi. So, speaking on an architectural base, you mentioned that there aren't any like hard set rules about the way a building can be constructed, and that it can be tweaked in the room. So, who chooses which rules can be tweaked, and is it manual, and does that bias the outcomes?
Well, that is the human dimension of city building that we keep kind of talking about, right? It is so embedded in the way decisions are made, and factors that go into it are political, has to do with money, has to do with a lot of factors that are frankly outside of the strict realm of the sort of design that we're thinking about. You know, I was previously part of another generative design company that generates buildings based on zoning rules, but the whole premise of that tool is predicated on buildings actually being built according to zoning rules, and that in fact isn't really the case for like 99% of the world, except for in New York City, where for some miraculous reason the rules actually stuck. I mean, in Toronto, for example, all of the most developments are negotiated with the city in terms of, you know, tweaking this and that zoning rule, and that's speaking for the majority of things happening in Toronto today. So yeah.
And technically, the way that actually works is whenever we have sort of a new idea for a constraint that we should implement, we will make that an input as opposed to hard coding values, obviously, so that if somebody that we're working with says, you know, I think that this is sort of the range that I would like, we could actually mutate those inputs within a certain value, or we could assign them a completely ridiculous value to see what would happen. So the goal of the tool is not to, you know, it's to expand optionality, not to cut down things, and we try to develop with that in mind.
Any further questions from the audience?
There are a bunch of things that don't really fit constraints very well. There are a bunch of lore, and they get lost and rediscovered all the time. I'm not in the field, but an example that surprised me, it's not completely relevant, but it's the kind of thing you see in architecture. Building a building where the stairs are more inviting than the elevators is really a little nudge towards health. So it's the opposite of optimization that we classically think of, trying to make things easier for people. So do you have a catalog of those bizarre ideas, and how
Do we?
I think, sure, that's a good question. I think that sort of gets into how opinionated of a tool are you trying to build, right? And so I used to lead accessibility strategy for Sidewalk, and one of the things we actually talk about is how do you make the most accessible way the most inviting way. And so stairs and elevators are actually a great example of how it's not super clear whether you should nudge everybody to take the stairs. If you're somebody who's using a wheelchair or a walker, you probably can't take the stairs, and you don't want to feel like you're shunted off to the side of a building because of the way that you get around. And so I think this is where it's so important for us to have domain experts and people who've built buildings in this way before who can point out some of these pitfalls so that the tool isn't naively suggesting something that has clearly already been decided to not be a good idea. And I think that is, you know, the tool is kind of like, what about this? Do you like this? And you can respond, it's like, no, it's not good because of this reason. Then you tweak the tool and you try it again. And it's like, do you like this one? And I think that is what, I mean, at its core, generative design is really about involving, you know, you generate something and you have a human involved in that process to choose what the next generation of it is going to look like. So yeah, nudges are something that obviously people choose to implement all the time. Usually depends on how much control you have over the building that you're building. And often a lot of those are things that, you know, we're not placing stairs yet. That's a higher level of fidelity often. There are questions of sort of which way your buildings face that do have to do with the objective functions of how much light would you like to get at which times of year.
But those kind of nudges are probably something we want to make very explicit, actually.
Right.
Like, we don't want to kind of, like, the generative design is not a tool in the behavioral modification sort of business, right? So, like, that is very much a value-laden part of the deciding what to build. And for that very reason, because of what we talked about today, that is something that we want to expose to people who are participating in this process.
Toby, can I get our last question?
Sure. Thanks again for the great talk. I love the first question you have up there, and I was just curious what your thoughts or insights are. I know there's a lot of work on like explainable AI and explainable algorithms, and it was mentioned briefly during the talk, but not in too much detail. And I think the interesting thing here is when there's both automation and human involvement, you want to understand the rationale from the algorithm's perspective of like, why did we arrive at this set of designs? Was it because epsilon was 0.91 versus 0.92? But also the human involvement too, especially if you're co-creating or involving the community. Like, why did they filter down to this set of results? How much thought and effort are you putting into that so you can learn from one project to the next?
I think the thing to say, correct me if I'm wrong, is that we're not quite at the stage of thinking about this part of the design yet. But for me, as a domain expert working within Sidewalk Labs, who is kind of a customer of this tool, one feature that would be great for me is actually a layer of features that supports human collaboration within these models, very much like Google Docs and Google spreadsheets that you were talking about, providing a traceable kind of history of the sort of human intelligence that went into a model, in addition to the sort of mechanical intelligence.
Yeah, and I will say actually this is something that our product managers, Violet Whitney and Okala Okena, spend a lot of time doing, is talking with us very specifically about which objective functions the score is most correlated with. Somebody actually spoke earlier to the fact that you seem to see a correlation of just pretty major changes, but that seem to be building higher and higher over time, and that's absolutely true. If you score something, if you say that you would like this amount of yield, this many square feet of each of these types of things, and you have a bonus for having more square feet, absolutely your algorithm is going to optimize for that. And so and you'll see that there are some objective functions that don't matter too much to the score that kind of end up being noisy, and there's some that correlate perfectly, and then there's some that correlate negatively. And so I think we're right now in the process of developing with customers what a great score function looks like that combines two things that are probably going to be opposing trade-offs and helps you decide what the right weights for them should be, and if you can find a good middle ground, or if you're going to bias toward one of them. So I think the correlation aspect is usually what we end up looking at on the technical side.
All right, that's all the time we have for questions, so please join me in thanking Siqi, Samara, and Brian once more.